All right, so today we'll finish up section 9.2, looking at polar, a little bit with polar graphing, and then I'm going to show you a connection between polar and parametric, okay, how to convert between the two. Okay, so remember, in polar, we write a point as r, comma, theta. R stands for radius, theta is your angle. Okay, so what I want to do here is look at a couple graphs. I'm going to start with r equals 2. So easiest way to figure this out is to just make up some coordinates where r equals 2. Notice here they don't say anything about theta. Theta can be anything you want. Just make sure r is 2. Can someone give me a coordinate where theta is anything you want, but r is 2? Andrew?
2, 0.
2, 0. Radians or degrees? I'm not sure. It's the same. 2 degrees. So 2, 0 degrees. There's a point on my graph. Can someone give me another another point that has a radius of 2, but a different angle?
245.
245. Right? R equals 2. So that one would be 2 units, right? It would be right there. Okay. I think once we do one more, you should probably be able to figure out what's going on here. Okay. Somebody give me one more point. Yeah.
135.
And what's your radius?
Oh,
2. 2. 135. So 2 units, right? 135 degrees. Theta can be anything, right? R has to be 2. If I draw every single point I could draw, what shape am I going to get? A circle. Right? That's why polar is really good for circles, because all you have to do is say r equals and put a single number. It's every single point that's 2 units distance from the origin. All of them. Okay. Yesterday I went through and I showed you how you would graph a circle as a function. I'll just show you how you would graph it today in polar. So you press mode, and I don't think we did this yesterday, but go to mode, go over to polar, and when you press y equals, notice now it doesn't say y equals. It doesn't look like it did for parametric. It's a new screen. It's r equals. Just put r equals 2. Now, the problem with drawing a circle on a rectangular screen is the same problem as if you watch like a standard TV channel on a widescreen TV. What happens to everything? What?
It gets like compressed.
Yeah, it gets compressed one way or stretched out the other way. So if I graph it like this, and I have to adjust my window a little bit. Let's see, we're in degrees, so let's go 0 to 360. I'll talk more about that in a second, but for now, you can just watch it. Did anyone have a guess why it's going so slow? We kind of talked about this. I'm plotting way too many points. It's going to get there, but it's going to take forever. So I'm going to press second off. I'm just going to stop it. And instead of going from 0 to 360, counting by 0.1s, let's count by 5s. Okay. Again, I'm going to talk more about this screen because you haven't seen it yet. I just want you to see the picture. And that's it. Single number to graph a circle. Okay. It looks kind of oval, but if you really look at it, it goes 2 units up, 2 units down, 2 units left, 2 units right. It goes 2 units in each direction. If you want to see it the way it should look, what you can do is press zoom, square. And then it makes everything look proportional. It shouldn't look stretched out. Now it looks a little better. I'm kind of seeing a little bit of jagged edges on it. Okay, when I start to see jagged edges, that means maybe I want to graph some more points to get a little more detail out of it. And if I do that, I think you'll notice the jagged edges kind of smooth out a little bit. It's about as good as I can get it. Okay? But that's a circle. Any questions on that one? Okay, let's try another one. Theta equals 2. Different than the last one. This isn't r equals 2. So r equals 2. You guys gave me a bunch of points that all have the same radius. Now you're going to give me a bunch of points that all have the same angle. The radius can be anything you want. But try to give me radii that fit on the circle. Don't give me like 107 because I can't fit that. Okay, so can someone give me a coordinate that has a radius of 2? 2, 0. All right. Like that? So, what did I say the angle had to be in this one? You're thinking the last type. Yeah, it's telling you that the angle has to be 2. All right? So, you can leave the first number as 2 if you want, but the second number also has to be 2. I kind of want to get an idea of what that is in degrees. So I'm just going to change it to a degree off to the side. So let's do 2 times 180 divided by pi. It's about 114 degrees, just to give you an idea of how to graph it. Okay, it's not necessary to convert it, I'm just trying to make it easier for me. So 2 units, 114 degrees, it's a little past 90. Okay, what would be another coordinate on that graph? Yeah?
Can you do different radiuses?
You can do any radius you want, but try to make it less than 4 because that's all I can fit.
Okay. So negative 3.
All right, so we could do negative 3, 2. All right, so that means we would start, and I'm going to erase this part after. We would go 3 units to the left, and now 114 degrees clockwise, counterclockwise.
How'd you get 114 degrees? Can you do that out again?
So it'd be about right there. Yep, to convert that to degrees, it's 2 times 180 divided by pi. That's how you convert radians to degrees. Okay, so there's that one. I think with the third one, we'll know what kind of shape we're going to get here. Can someone give me one more coordinate that has an angle of 2 but a different radius? Colleen?
Sorry.
Can you give me one more point that would be on that graph?
Just
Sure, negative 2, 2. So this time we're going to go 2 units left and 114 degrees counterclockwise. Oh, right there. Okay, I can keep going, but does anybody see what kind of shape we're going to get here if we keep doing these points? Yeah. We're going to get a line. Yep. We're going to get, my angle's not perfect, but the idea is you're just going to keep getting points that have the same angle, but different radius. So I know mine's not perfect, but that's the idea. That you can't draw on the calculator easily. If you press the button, you get r equals. You don't get theta equals as a choice. So that's something you have to do by hand. So the point, theta equals a number, straight line through the origin. R equals a number, circle. Questions on difference between these two graphs? All right, so next thing we're going to do is look at a little more complicated looking graph. Once we do it the first time, you'll know in the future what it is. But We'll kind of go through it together right now. And what I'm going to do is help you set up a table of values so you can kind of see what's going on. And what we're going to graph is r equals 3 plus 3 sine theta. Now, if this part wasn't here, if it was just r equals 3, what would it be? It would be a circle. Well, plus 3 sine theta is going to change the shape of it a little bit. So it's going to be kind of like a circle, but it's going to do something a little different. Okay, so the directions will probably make more sense, I hope, as we just actually go through and do it. Okay, first thing we have to remember is that anytime we graph something with sine or cosine, just like when you had t as a parameter, you have to tell the calculator what's the lowest value, what's the highest value. I don't have a t-min and a t-max anymore. T-min and t-max, that's parametric. This is theta-min, theta-max, but it's exactly the same thing. What's the lowest value for theta I should be using? What's the highest value? Now, on a graph that draws over itself, it doesn't really matter how high you set it. Like on a circle, that's 0 to 2 pi. That's 0 to 4 pi. It's just going to draw right over itself. On a spiral, you would start to see it more, because spirals don't draw over themselves. You see more of a spiral. Okay? This is going to be the kind of graph that draws over itself. Okay? So we only need to do one revolution to get a nice picture. All right, so I'll come back to R in a little bit. First, I just want to look at this picture. That's a picture of sine. Okay? The highest it goes is 1. The lowest it goes is -1. And it goes through all the values in between. Any questions on that picture? Peak is at pi over 2. It hits 0 at pi. It hits its lowest value at 3 pi over 2. And then it starts over back where it started when it gets to 2 pi. Okay, so we're going to use that. And now we're going to set up this table. What we're going to do is examine that graph in 4 different sections. Okay, because there's really 4 things happening here. In this part, the graph is starting at 0, and it's going to its highest value. Okay, that'll be the red part. In the green part, it's starting at its highest value, and it's going down to 0. That's going to be in that section. From pi over 2 to pi, it's going down. From pi to 3 pi over 2, it's still going down. And it's hitting its lowest point that it's ever going to hit. That's from pi to 3 pi over 2. And then from 3 pi over 2 to 2 pi, I'll just leave that in black. It's going from its lowest value back up to 0. So let's just do that one in black. We're going to look at each section one at a time. Okay, I kind of said these as I go, but we'll write them down now. Okay, let's start with sine, between 0 and pi over 2. So in the red section, where does sine start and where does it finish? It starts at 0 and it finishes at 1. It starts at 0, it finishes at 1. Now, we're graphing r equals 3 plus 3 sine theta. I just copied it down here so we could see it. So now we know what's happening right there. The thing that I just kind of wavy underlined is starting at 0 and it's going up to 1. So let's figure out what our radius is going to be in this section. The smallest value that sine will ever be is 0. Let's plug in 0 for that box. What's 3 times 0? 0 plus 3. 3. So in this section, our radius, actually, you know what? I'm going to do it like this. It's starting at 3. And as we head to 90 degrees on the circle, when we graph it, the radius is going to grow. Highest it can go up to, well, the highest value sine hits is a 1. What's 3 times 1? 3? Plus 3 is 6. So when we draw this, the radius is going to be growing from 3 to 6. So it's going to get bigger as we draw it. Right? We'll come back to that. But let's look at the next section. Right. From pi over 2 to pi, that's the green section. My sine is going from 1 to 0. It's decreasing. So now let's see what that means in terms of my radius. In this section, we're starting at 1 for sine value. What would you get for a radius if you plug in 1 for what the box is around? 6. So in this section, the radius is shrinking from 6 down to sine could be lowest is 0. 0 times 3 is 3, plus 3. 0 times 3 is 0, plus 3 is 3. So in the next part of this graph, we're going to have a radius that's getting shorter and shorter. Okay, it's going to be the second part. Okay, third part. Blue section. What's the sine value starting at and going to in the blue section? 0 to negative 1. All right, so in terms of my radius, it's going to start with the sine value is 0. 0 times 3, 0. 0 plus 3 is how much? 3. And the last part, Cameron, what's the lowest value that sine hits in the blue section? Negative 1. What's negative 1 times 3? Plus 3? 0. So in this section, the radius is shrinking all the way to 0, which means this graph is going to go right to the origin. If you have a point that has a radius of 0, that's when I kind of made a joke there and put the point and just rotated it at the origin. It just stayed right where it was. Okay, and now let's look at the black section. In the black section, sine is going from negative 1 to 0. It's going back up again. Okay. What would my radius be in this section? If sine is going from negative 1 up to 0. It would be 0 to 3. Okay, so now we kind of have an idea of what's happening to the radius in different sections. So now we're going to try to sketch it. And I'll do the best I can, but it's a curve, so it's not the easiest thing to always sketch. So when we start at 0, that's when my radius was 3. Okay? So basically just match these numbers up. When you have an angle of 0, that's the shortest the radius is in the red section. So that's 3. So I think I have a grid. Yep. 0, 3. As I head towards pi over 2, what's pi over 2 again in degrees?
Pi over 2 is
90. So as I head to 90 degrees, my radius is going to grow from 3 to 6. So when I get all the way up to 90, my radius is up there. So what this kind of looks like, I'm not going to keep these here, but Looks kind of like that. As you move from 0 to 90, the radii are getting longer and longer until they hit their longest value at 6. Okay. I can keep those there, but you don't need it. That's not really part of the picture. I'm just trying to show you. Okay. What about in the next section? As I go from pi over 2 to pi, what's happening to my radius? Brandon?
No, yeah, but I was not paying attention.
So as I go from pi over 2 to pi, what's happening to my radius?
It's going down.
From what to what?
Pi over 2 to pi.
That's my aim.
From 1 to 0? Or the, I'm not quite sure. So 6 to 3. I was not paying attention, I'm sorry.
Anyone help him out? What's happening to the radius from pi over 2 to pi?
Doubles.
It's what?
Doubles. From 3 to 6.
No, divided by 2, doesn't it?
Yeah, just what's the pattern? It's at pi over 2, what's the radius start at?
90.
Well, pi over 2 is 90. So at 90, the radius starts at 6. Okay? No?
Jeez, man.
So basically, to graph this, you have to plug in different numbers for theta. If you want, plug in every number from 1 to 360 by hand, do it all out, and write down all 360 points and graph them. But that's going to be really hard. So what we're trying to do is look at just the points that are where things are changing. Okay? We're looking at where the radius is going up. Okay, so here sine is going up, then all of a sudden it switches to going down, goes below the axis and keeps going down, and then it switches again and goes back up. So I'm just trying to look at the points where things are going to change. In the red section, it doesn't make sense to find any other points in the middle because it's not doing anything different. It's still going up in the middle of the red section. Towards the end of the red section, still going up. Towards the beginning of the red section, still going up. It's always going up in the red section. So all I really need to do is find where does it start and where does it stop in the red section. So to do that, you have to take what you're graphing and plug in where you start and where you stop. Where you start is 0, and where we stop is 1. That's the highest it ever hits. So this box right here is starting at 0, that's the sign, and it's going up to 1 in the red section. So what does that mean? If it starts at 0, you do 3 times 0 plus 3. That tells you where the radius starts. And then the box, the highest value it would ever hit is 1. 3 times 1 is 3, plus 3 is 6. Now, it's not going to keep going past 6, because then after that, the sine function starts dropping. So now, this box isn't going to go from 0 to 1. It's going to start at 1. And in the green section, it's going to go down to 0. That's what's happening to the sine function. So what does that mean? Well, now you can plug it in. 3 times 1 is 3, plus 3 is 6. So my radius in this section starts at 6. And as I head to pi, my sine function goes to 0. 0 times 3 is 0. 0 plus 3 is 3. So the radius is decreasing in this section. Does that make any more sense? Well, we'll keep going. We'll do the next 2 sections and see what happens. Okay. So at pi over 2, my radius is 6. I already have that right there. That's exactly what I ended with last time. At pi over 2, it's at 6. At pi, it's at 3. Where's pi? 180. So when I get to pi, my radius is going to shrink back to 3. It's basically like a mirror image of what just happened. As you travel on the circle, radius is getting shorter and shorter and shorter. Okay, so the first part of our graph kind of looks like this. And the second part, kind of like a mirror image. Okay, I'm just going to take these out of there. So as you travel from 0 to 90, radius is growing. 90 to 180, radius is shrinking. Okay, now in the blue section. When I'm at pi, what's my radius? 3. Right? We had that where we ended last time. You always pick up in the next section where you ended in the last section. So pi 3. Already got that. Kind of makes a little more sense? All right. As we travel to 3 pi over 2, what's happening to my radius? It's starting at 3. It's going to 0. So what that means is it starts at 3, and as you continue drawing lines towards 270, the lines get shorter and shorter until they basically hit 0. So this section kind of looks like that. They start at 3, and as you head towards 270, we're spiraling kind of into the origin because it's getting shorter and shorter. And the last section is going to be a mirror image. As we go from 270, well, let's start there. Where's my radius at 270? 0. And now, as I head all the way around to 360, what's happening to my radius? It's growing to 3. Okay, so what that's going to look like? Kind of like this. As you travel towards 360, the radius is getting longer and longer, till finally, when you go all the way around, it's at 360. So that section, you kind of look like that. Okay, I'll just move all this out of the way. I had it better the first time. That's pretty good. Did anyone see what that kind of looks like? A heart. That's what it's supposed to look like. This one's upside down. It can be right side up. Depends on the picture. But because it kind of looks like a heart, they call it a cardioid. Okay, that's the name of that graph. Now, when you graph it on a calculator, depending on how you do it, you might make it look more squished or stretched out. So it might not look like a heart. Like this section may end up looking a lot rounder. Okay, it depends on how you set your window. Okay, so any graph that's of the form a number plus or minus a number with sign, that's a cardioid. This is 3 plus 3 sine theta. 2 plus 2 sine theta.
Wait, so I have a question. So if this were to be on, like, is it going to be like set up like that on a test, or do we have to like? I'm so confused.
What's your question?
Never mind. I'll just figure it out.
So if we want to graph it on the calculator, just type in 3 plus 3 sine theta. Okay, I have to set my window. I don't go any higher than 6 in any direction, so that's probably okay. That's zoomed out more than I needed. but make sure you go from 0 to 360, or 0 to 2 pi if you're doing radians. Okay. I'll show you what happens if you don't. Okay, so there's the graph we just drew. Again, it does look more rounded than mine. I kind of exaggerated the heart a little bit to make it look more like a heart. If you only go, let's say, 0 to 180, what's going to happen? Bless you.
Thank you.
You're only going to get those two sections. Okay, you're going to lose everything else. So it's 0, 90, 180, done. Okay. Didn't draw the rest of it. Okay, if you change these numbers, you just have to keep them the same for it to be a cardioid. But if you make that a 6 and a 6, to show you what happens, you get a bigger cardioid. It gets bigger, but it's still a cardioid as long as you keep the two numbers the same. Now, if you make them different, weird things start to happen. This is not a cardioid anymore. Okay, what's going to happen here? I think it's going to loop back on itself. Yep. So now what happens is the loop actually kind of comes back on itself. We're not going to get into graphing things this complicated, okay? Especially by hand. Even cardioids, you can really just use your calculator. I'm just trying to explain why it looks like a heart. Any questions on it? No? Okay, again, it takes practice.
Actually, I do have a question.
Yeah.
How do you like? So you see how it's like smaller, I guess, like the things that go like this.
Yeah.
Do those stay small, or can those get bigger too, or is it just the top that gets bigger?
I think really anything can change. Depends on how you do your numbers. Let's try this one. It's usually bigger though towards the top. Okay, so what happens there, it almost kind of flattened it out. So it actually made the bottom ones even smaller. If you zoomed in, you'd see they curve in a little bit. But I think that's usually the pattern where the bottom is smaller. Yeah. All right, so let's move on from cardioids. All right, so what we're going to do next is we're going to convert an equation that's in polar to rectangular. Okay. Good thing about this is we already have all the formulas we need to do it from yesterday and Monday. Exciting, I know.
What?
So x equals r cosine theta, and y equals r sine theta. Those are two formulas we're going to use that we already know. X squared plus y squared equals r squared. That's our Pythagorean theorem formula. And theta equals inverse tangent y over x. So we're using all the stuff we already came up with yesterday. Okay. As a reminder, what do you have in polar? What two letters? You have a radius and a theta. And what about in rectangular? An x and a y. So yesterday we converted an individual point from polar to rectangular. Now we're going to convert an equation. But it's pretty much the same thing. Okay, I want to convert that to rectangular. What is that? 3 plus 3 sine theta.
A heart.
It's a heart. It's a cardioid. It's the one we just, I think it's the one we just did. So my goal is to convert this to something with x's and y's. Okay, let's start with this. Let's get rid of sine. Do I have a formula up above that has sine in it somewhere? Well, Mike?
Y equals r sine cosine.
Yeah. y equals r sine theta. How would you get sine theta by itself? Right here, remember multiplication?
Oh,
Divide by r. Y divided by r is sine. Question on that? Okay, so plug that in. Let's change sine to y divided by r. It doesn't get rid of everything, but at least now we have a y in there, and that's the goal. I want to have x's and y's when I'm doing it. So I'm substituting for everything that's not an x or a y. And I just decided to start with this. You have to do this too. You have to get rid of the r, but I'll do that next. So we have 3y over r. Okay. Now let's look at the r. You know what? I don't like having this divided by r in the bottom. So what could I multiply everything by to get rid of that r in the bottom? R. Yeah, let's just multiply everything through by r. At least to me that looks a little simpler now because I don't have a fraction in the middle of it. I still have to get rid of these r's. But let's look at r squared. Do we have anything with an r squared in it? What does r squared equal? Perfect. That's going to totally get rid of r squared, and now we'll have x's and y's. X squared plus y squared. The 3y is okay. Only thing I have left is 3, and then I have an r next to it. Well, if r squared is x squared plus y squared, what would r be? Think about it. If you got rid of that exponent of 2 on the r, how would you do that? Square root. So r is the square root of x squared plus y squared. I didn't really leave enough room, but... So we just substituted x squared plus y squared for r squared. And for r, the square root of x squared plus y squared. And that's it. We stop right there. That's the equation of a cardioid written with x's and y's. That is not something you could plug into the calculator because there's no way to get y by itself there. Okay? That's why when we do cardioids, we do them in polar, because the equation is much nicer than it would be with x's and y's. But that's it.
you need that part on the left, you know?
You need that whole box.
Okay.
Yep. That's, this part right here was r squared. R squared equals x squared plus y squared. So this time I didn't even use inverse tangent. Most of the time you don't need it. I didn't have a cosine in this problem, so I didn't need that either. If this was a cosine, then I would adjust and do it for cosine. But that's how you change something from parametric to function. Hopefully I wrote that down. Or polar to rectangular. Yeah, not
How do you know
parametric.
when you're done?
You're done. You don't have when you have all x's and y's. If you still have an r in the problem, you're not done. If you have a theta in the problem, you're not done. You can have numbers, x's and y's, and square roots, equal signs, things like that's okay. No r's, no thetas. Okay, so that's polar to function. Polar to rectangular. Okay, your calculator doesn't call it rectangular. If you press the mode button, it says function. Okay, so I'm going to show you another conversion. Okay, the last one we did was to change polar to a function. Now I'm going to show you how to change polar to parametric. We use these two formulas. The first thing you have to do when you go from polar to parametric is you have to change theta to t. Okay. Polar uses theta. When I put it in parametric, it uses t. So just change your thetas to t's first. Okay, second thing. When you write something in parametric, you have to have two equations. One for the x, one for the y.
Is that a T or an
Those are all t's. The equation for the x is whatever you had right there times cosine. So you just take whatever they give you, put a cosine next to it, that turns it into the x. Take whatever they gave you for the original problem, put a sign next to it, that turns it into the y. Okay, so again, just take whatever they gave you, copy it down for each equation. In the x, put a cosine next to it. In the y, put a sign next to it. Okay, this is a lot easier to explain than trying to graph a cardioid, because when you're graphing a cardioid, you have to actually think a little bit and understand what's happening. Here, you can pretty much just say, okay, he said to copy this here, write cosine here, write sine here. There's no thinking at all. You do the same thing every time. All right, so let me leave that up and try this one. So the equation they gave us is r equals 7 sine 2 theta. First thing you do, copy it down in each spot. But I'm going to change theta to what?
T.
T. I'm going to change theta to t. So what am I going to put first on the line that says x equals? I think you're...
Is it F2T? Or, no, yeah, I have no idea.
So this is our f of theta. That's our function. 7 sine 2 theta.
Wait, so which ones are the F's and which ones are the T's?
they're all
I'm
T's.
sorry.
That's f of theta. The t's are used in parametric, the thetas are used in polar.
Okay.
So like on the left, F of T. Okay.
You need to take your function and put in t's in place of theta.
When you said all
Yeah.
T's, I thought
Yeah, me
all
too.
T's.
So that's what makes me.
So what would be the first thing we write on the x equals line?
2 theta.
I'll give you a hint.
7. I don't.
7 times
I just
2
used cosine.
No cosine here. This says sine.
Oh,
There's no
then
cosine.
sine.
7 sine.
Wait. Oh.
So whatever's here,
Oh, 7.
write it there and write it there.
7 sine 2.
7 sine 2. And we're changing theta to t. And what else is next to it? Cosine t. That's it. And how about for y?
7 sine 2 t cosine 9.
7 sine 2t. And what's next to it? Sine t. what we just did is we changed an equation from polar to parametric. I'm going to graph it and try to show you that they look the same. I'm going to graph 7 sine 2 theta. 7 sine 2 theta. Okay, and show you what it looks like. Let's just do zoom 6. Okay, that's what the graph of 7 sine 2 theta looks like. Any questions on that picture? So all I did was type in 7 sine 2 theta. Okay, now I'm going to go to parametric, which is that separate x and y. And I'm going to type in what you just told me. 7 sine 2t cosine t. And I'm going to, on the y, I'm going to type in 7 sine 2t sine t. And I'm going to do zoom 6 just like I did before. They're exactly the same picture. And they should be, because we converted from one to the other. So all you have to do to convert it is take what you have in the box, copy it down twice with t's, and then in the x you put a cosine next to it, and in the y you put a sine next to it. If you forget to put the cosine or sine next to it, I'll show you what happens. Let's get rid of the cosine and say you forgot. You get nothing like you're supposed to really get. It's a little different. Okay? So you got to make sure you put the cosine and sine. And that's it. That's all you have to do to change from polar to parametric. Copy it down, put a cosine next to it. Copy it down, put a sine next to it. Okay, and this particular graph is called a 4-petaled rose. Okay, that's the kind of graph that it is. So yesterday I asked Brandon his favorite number. He said 82. That's a few too many petals to draw. But basically, you always draw double the number of petals as that number right there. So if you put in a 4, you're going to get 8 petals. Unless it's odd. If you put in an odd number, you actually get exactly the number that you want. So I'll show you with a 3. Let's put, let's make it 3 theta. So you might think, oh, is it going to double and get 6? No, you do get 3. So if you put in an odd number, you get exactly that. Even, you get double. And the length of each petal, that line segment that I just drew in red, it's the absolute value of the number in front of it. So these petals have a length of 7 units. Okay, so what I might do is give you an equation like that and just say what would be the length of each petal. Okay, that would be 7 units. How about if I did this? R equals 12 sine 4 theta. What would be the length of each petal there? 12. How many petals would I have? 8. Yes. What if I did -3 sine 5 theta? What would be the length of each petal?
-3.
3. So length of each petal would be 3. How many petals would I have? 5, exactly 5. Yeah. So for this kind of graph, you just have to know if you change these numbers, what effect does it have? How many petals would it have? How long would it make each petal? Okay. So any questions on that type of graph? Okay, and then our last graph is a spiral. Okay, this one in particular, they call it the spiral of Archimedes, and it's r equals theta. So let's just plug it in, see what it looks like. So what you're doing is you're setting the radius equal to a variable. That means the radius can change. It's not a fixed number. Well, if I do zoom 6, it goes off the screen. So let me zoom out a little bit. Still going off the screen, so I'm going to just keep zooming out until you can finally see it. Maybe one more time. Okay, so there's one revolution of my spiral. To go around one revolution, how far is that? In degrees or radians? 360. So if I look at my theta min and theta max, I'm going from 0 to 360. What if I did 720? How many revolutions of the spiral would I get? I'd get 2. It's going to go off the screen. There's 1. Yeah, it goes off the screen. But now you're going to get 2, and it's going to stop right there. Okay, so that's the spiral of Archimedes. Okay, so what I'm showing you here is graphing it with different parameters. I just graphed 0 to 2 pi. That's the first one I did. 0 to 720. That's 0 to 4 pi. Okay. And let's go all the way to 8 pi, but I'm going to do it in degrees. So that's 720 doubled. How many revolutions of the spiral am I going to get now? 4. Okay, I can hit graph, but you're going to see 1, 2, kind of part of the third one. So just zoom out. There's 1, 2, 3, 4. 4 revolutions of the spiral. Okay. So changing theta min and theta max, it just controls how many times it revolves. That's all. But the bigger you make it, the more you have to zoom out your window. Because I had to zoom out all the way to 2500. So that's the spiral. Okay, so any questions on that stuff? Anything like, if we saw this on a test, what kind of question would you ask about it?
Would that question be how many revolutions do you see?
This kind of question, what it would be is it would be a multiple choice. I would give you the graph. I would say, here's the interval I want you to do, and you'd have 4 pictures to pick from. Which one is correct? That's how you'd see a question like that. Yeah. I probably wouldn't ask you how many times it spiraled, but you'd have 4 choices of pictures. Okay. Any other questions about? Same with the flowered 4-petaled thing. I'd probably give you a graph, give you 4 pictures, and say which one is correct. All right, so homework, it's probably not going to seem as difficult as what we did in class because you can use your calculator on every question, so you don't have to sketch anything by hand, which I think was the hardest thing for most people.
Wait, can you remove your head out of it?
Move what?
I'm talking. He's way taller than me, so it's hard to see. It's okay, it's not your fault, it's...
Okay, so we'll take a look at the homework tomorrow. If anybody needs extra help, I will be here today if you can come. Don't forget, if you have a test to make up, you have 2 more days to get it done.